Okay, let's start. Today we have special guest from France, Dr. Achrène Dyrek from Astrophysics Department, CA Paris-Saclay. Please welcome.
Thank you. Can you hear me well first?
Yes, we
Okay,
can
great.
hear you well.
Well, thank you very much for having me. So my name is Achrène Dyrek. I'm a postdoc at CEA in Paris. I've just completed my thesis in exoplanetary atmospheres with the James Webb Space Telescope. And today I will be giving a 40 minutes talk on the work I've been doing during my thesis and the contributions that we did at CEA here with the James Webb Space Telescope on the field of exoplanetary atmospheres. So here is the outline of the presentation. I will start by giving the context of this research, talking about the exoplanetary atmospheres before James Webb and now that we have James Webb, and the role of one of the groups, which is the MIRI Guaranteed Time Observation team. Then I will present results that we obtained on massive objects, substellar objects, which are brown dwarfs. And then I'm going to be down with the smaller planets like TRAPPIST-1b, which is a rocky one. And finally, I will talk about one of my main contributions, which is the work on photochemistry in exoplanetary atmospheres. And I will give a conclusion and some perspectives. So let's start with exoplanetary atmospheres before and with JWST. So we have discovered so far 5,500 exoplanets. And when you put them in a diagram that shows the mass as a function of the distance to the star, so the semi-major axis, you can see that these exoplanets are really diverse and really different from the planets of our solar system. So in red, you have the planets of the solar system. And what you can see is that there is no analogues of some of the planets, such as the Earth or Mercury. And you have new populations coming out. For example, you have these populations, which is a population of very young and really massive exoplanets. You have this population as well, which is a population of exoplanets that orbits really close to the star. So we have no analogs. Yes, there is a phrase. Oh, okay. And so these exoplanets, they do not have analogs in our solar system. They're really peculiar. We call them hot Jupiters, so like Jupiter, but really close to the star, or super Earth or sub-Neptunes. And they have peculiar properties. Their period is really short, from 1 to 10 days, and their temperature is quite high, from 200 to 2000 Kelvin. And so when you see this population of exoplanets, you want to understand how they form, how they evolve, why they're here. And so we have main questions in the field that we want to answer. First, what are the formation and evolution processes of this system from the protoplanetary disk to the systems as we know them now, and including our own solar system? We want to understand the different compositions of these exoplanets, and we want to understand their structures. And finally, we want to understand if our solar system is unique or representative of all of these systems that are abroad. And to start answering these questions, what we started to do is to characterize their atmospheres. So the atmosphere brings a lot of answers regarding the molecular and atomic composition, regarding the different pressure, temperature profiles and conditions, and the dynamics of an exoplanet, about the winds, the clouds, and the recirculation. So to do that, we have different techniques that we use, depending on the kind of exoplanet you are observing. For example, if you observe exoplanets that are really far from the star, you can do what we call direct imaging. So you have enough angular separation to actually have an image of the planet or a spectrum and characterize the emission of its atmosphere. And if you are really close to the star, there is no way that you can separate the star from the planet. And so what you do is time separation technique, where you see the modulation of the presence of a planet of the flux of the star. So I am going to explain a bit more the time separation technique, as it is a bit different from a simple image. So what we use is what we call the transit technique. So it is quite a simple technique, actually. What you do is you observe a star, and if you're lucky enough to have a planet in the line of sight of your telescope, you can observe the moment when the planet comes in front of the star. And so at this moment, you will have your flux that is going to be down a bit. And so this is what you can see here, and this is what we call a transit. And so this is a very common technique in the field. And through this technique, we have discovered more than 3,000 exoplanets. And so what is really interesting is that this transit depth that you can see here is actually dependent on the wavelengths. And so if you start observing this transit depth at different wavelengths, you can do what we call transit spectroscopy. And this is directly linked to the composition of the atmosphere. So I am going to give an example to explain the link between the composition of the atmosphere and the transit depths. So let's imagine that you have an exoplanet with an atmosphere made of water vapor, and you observe it. So on the left, you have the star, then you have the exoplanet, and on the right, you have your telescope. And you observe your exoplanet at a given wavelength range, which is named A. Then you will observe the same exoplanet at another wavelength range, which is B. And so what happens is that some of the molecules are going to observe at given wavelengths. So in the first case, the atmosphere of water vapor is absorbing at this given wavelength range. And on the other case, it is not absorbing, and so it will be transparent. And so what you can see here is that the radius of the planet is going to vary as a function of wavelengths. So in the first case, it will be increasing as the atmosphere is blocking the light from the star. And in the other case, it will be decreasing as the atmosphere is completely transparent to the light of the star. And so if you put these variations as a function of wavelengths, you will have a spectrum. And so this is what we do to get a spectrum of an atmosphere. We report the variations of the radius of a planet, and we get the composition. So for example, in this exoplanet, you have water vapor, and this has been done using the Hubble Space Telescope. So I hope it was clear to understand how we characterize the atmosphere of an exoplanet using the transit spectroscopy technique. So far, if we look at the state of the art, we had two main missions that were observing exoplanetary atmospheres. You had the Hubble Space Telescope and the Spitzer, as well as some ground-based telescopes. On the right, you have a bunch of different spectra of exoplanetary atmospheres. And so what you can see in this spectra is the wavelength range that was accessible before. So mostly you could have found water vapor thanks to the Hubble Space Telescope, or potassium or sodium at the visible wavelength range. You had, after 2 micron, Spitzer that did some work, but not in spectroscopy, in photometry. And so in photometry, you only have hints of molecular detections. But what happens is that the molecules that you have to find in exoplanetary atmosphere that are supposed to be there absorb in the near and mid-infrared. If you look at the peak of absorption of these molecules, they are mostly in the near and mid-infrared. And so there is a lack of telescopes to actually observe in the infrared to detect these molecules. So you can see, starting from 2 micron, there is no spectroscopic data available. And so there was a need for near and mid-infrared facilities to actually carry on this work and observe other molecules than water vapor or potassium or sodium. And so the answer to that was the James Webb Space Telescope. So for those who don't know, the James Webb Space Telescope was launched 2 years ago from French Guiana in Kourou. And it has a very peculiar wavelength coverage because it's a very wide wavelength range. You go from 0.5 to 28.5 micron. So this is quite new because you have this huge spectral coverage, and you have 4 instruments on board covering the whole wavelength range. So you have NIRIS, NIRSpec, NIRCam, and MIRI. It is a unique observatory for atmospheric characterization because you have this wide wavelength range where you can actually look for these signatures of molecules that are supposed to be in atmosphere in these atmospheres. And what's really important with the James Webb is the sensitivity. So the mirror is 6.5 meter diameter. So with this high sensitivity, you can start observing smaller exoplanets, such as rocky exoplanets, and temperate one like the Earth. So with this observatory, we are going to do a lot of work on exoplanetary atmospheres. So in that context, we have a group which is called the Guaranteed Time Observation that is made for the institutes that contributed to the instruments. So on the left, you have one of the instruments, which is the mid-infrared instrument, MIRI, and you have here the optical path. So it was at CEA, and it is here the test model that you see. And so for the institutes that actually built the instruments, in return for the development, you have observations that you can make. And we had 400 hours of observations. And among the observations, so it is really large. It goes from galaxy observations to interstellar medium and exoplanets. And so among these hours, you have 100 hours dedicated to exoplanets. You have 28 laboratories involved in Europe. And this team is led by Pierre-Olivier Lagage, who is a professor here at CEA, and Rens Waters, that is a professor at Radboud University in the Netherlands. And so with this team, we have been doing a lot of work characterizing the exoplanets with James Webb. So let me talk about the mid-infrared instrument. So it is quite unique as it has different modes in the mid-infrared. So you have 4 observation modes divided in 2 categories. So depending on the way you want to observe exoplanets, so if you want to do angular separation to actually separate the star and the planet and make an image of the planet, or if you want to do a time separation technique like the transit technique, you have different modes. So on the left, you have the medium resolution spectrometer, which is a very interesting mode. You are going to choose a zone in your detector and do spectroscopy of different parts of the image so that you can isolate your exoplanet and make a spectrum, an emission spectrum of it. So it's a very strong technique that has a medium resolution. So it is up to 2000 resolution. So it's quite interesting. And you have a coronographic mode when you are going to actually put a mask on the star to reduce the luminosity of the star to actually make an image of the planet. So these 2 modes are really strong to image planets that are really far from the star. But if you can't do that, you have this transit technique. So you have another mode, which is a low resolution spectrometer, where you're going to do time series of observations and do a spectrum of it, or a wideband imaging when you have no sensitivity to do a spectrum. So you can do just imaging in wide bands in different wavelength range. So all of these modes have been used to actually characterize exoplanetary atmospheres. So here I've been showing the different objects that you can characterize. So starting from the right to the left, and the more you go to the right, the more the distance to the star increases. So on the right, you have all these massive substellar companions or even free-floating objects that do not orbit around a star. And to observe them, you can do direct imaging using the medium resolution spectrometer or the low resolution spectrometer. Then if you go nearer to the star, you have these young hot Jupiters, which can observe with the wideband coronagraphy. And then you have these transiting exoplanets that you can observe with photometric modes, like wideband photometry or LRS transit spectroscopy. And so what I'm going to do here is to present three main results in the three different population of exoplanet that we've been observing. And so let's talk about the key results we obtained with this guaranteed time observation team. So first, go to the substellar companions, and I want to present the work we've been conducting on a brown dwarf, which is named WISE G1828, which is here on the image, and it is located to a distance of 14 parsec, and it is quite cold. It's 300 Kelvin. And so what we wanted to understand is the characterization of the atmosphere of the brown dwarf. So there is always this limit that we don't really understand of the upper bound of exoplanetary masses. So we don't really know what is the limit between an exoplanet, a star, and what we have in between, which is a brown dwarf. And so we want to understand the atmospheric composition in emission to start constraining the different formation scenarios to understand which one is a stellar formation scenario or a planetary formation scenario. And so this is what we tried to do with the medium resolution spectrometer. So this is the spectrum we made of this brown dwarf. So it goes here from 5 to 18 micrometer. And you have, so in dark, it is the JWST MIRI spectrum. And in red, it is the model. So you see that the model fits quite well the observations. And so what's really interesting in this spectrum is the discovery of several molecules. So you have methane, you have water vapor, you have ammonia, and most importantly, you see the isotopologues of ammonia. So let me zoom in. So this is between 9 and 12. And so what appears here is the fact that if we zoom in again, so it's the fact that you have not only ammonia, but different isotopologues of ammonia. So the 14 and 15 isotopes of ammonia. So in blue, you can see here, it's not really obvious, but if you look at it, you can see it. If you fit the data without the isotopologues, you actually don't quite fit the data well. And so this proves, obviously as a model-dependent way, the fact that there is actually different isotopologues in this brown dwarf. And so this is kind of the power of MRS with this resolution, that you can actually see these isotopologues. So it's interesting because isotopologues, we know that we have detected them in different objects. So in the prestellar cores, right, in this interstellar medium, we know that there are isotopologues of not only ammonia, but other isotopologues in disks, so the protoplanetary disks, in planets in our solar system, and in comets and meteorites. So it's the first time that you can actually observe it in a brown dwarf. So in this object that is in between a star and a planet. So it is a very first time that we can do that. And so we can't really say anything about it. We can't really know what it means for now, but it is a first detection. And so if we push it a bit further, we can start talking about theory of planet formation. So the amount of isotopes that you have, so here the 14 and the 15, depending on this ratio, you can start constraining the amount of ammonia or N2 that is produced as a gas phase or liquid or solid phase, grains phase. And depending on the different ice lines, the amount of N2 that is actually produced is not the same. So if you constrain the ratio of isotopes, you can actually constrain the location of formation of your brown dwarf or exoplanet. So for now, we have quite large error bars. So if I go back, you can see the error bars is really large. So you can't really know where you're located. But if we start using the MIRI to characterize brown dwarfs, we can start doing this work. So I think it's a very interesting way to start separating different formation scenarios between stellar formation scenarios and planetary formation scenarios. So this was the first example of the work we've been doing. Now I am going to move to a completely different object, which is a temperate rocky exoplanet. So if we move forward in the category of exoplanet, now we go really, really close to the star. And so you can see now the star is red, which means that this transiting exoplanet that I'm going to talk about orbits a very small and cold M dwarf. So I am talking about the TRAPPIST-1 system, which is a very, very interesting system. So it is a system of exoplanets that orbit a red dwarf. So this is a very late system. So you can see the age here is 7 billion years. And the star is really, really small. So you can see here the mass compared to our sun. So it is 8% of our solar mass and 11% of our solar radius. So it's a very, very small star and a very cold one. And so around this star, there have been discovered 7 rocky exoplanets, really similar to the Earth. So you can see here on the bottom the radius and the mass. So we're really close to the Earth mass and radius. And also you can see the distance to the star. So this is a very, very compact system. So you can see the planets are really, really close to the star. And so this is interesting because they're facing huge tidal effects and they are synchronized. So this is an interesting, so their orbits are actually synchronized one with the other. And so their period are synchronized. Also, when you see the period, it's really short. So the latest one orbits actually in 20 days. So it's a very, very different system from ours, even though we do have temperate planets in our system, this one is completely apart. So as they're rocky and as they're temperate, a lot of researchers have been really concerned with this exoplanet and they want to understand not only the formation and the evolution of the system, but also, of course, the habitability of the system, right? And so here are an example of papers that have been written in the subject, but I think there are like more than 200 papers on it. So it's like a system that has huge interest in the community. And so what's really important with the system is that it is a small one. These planets are really small. So before James Webb, no atmosphere has never been probed around a temperate rocky exoplanet. So with James Webb, we have the possibility to do it. So what we wanted to do is to observe the planet when it passes not in front of the star, but behind the star. Here you can see it. And so when you see it, as these planets are really close to the star, they are tidally locked. So it's like the moon and the Earth. So when it goes behind it, you can actually see the emission, what we call the day side of the planet. And so if you can constrain the emission, you can constrain the temperature. And if you have an idea of your temperature, you can constrain the presence of an atmosphere. And so this is what we wanted to do. So what you can see here is a theoretical spectrum of the atmosphere of this exoplanet in emission. And so what we did is we observed it with the mid-infrared instrument in the CO2 emission band at 2 different wavelength range with wide band photometry. So at 12.8, here you can see it, and at 15 micron. to observe if we actually see CO2 or any other things, or the presence of an atmosphere, or on the contrary, if it's totally a bare rock. So that was the goal of this proposal. And so this is what we did. So this paper is being published, so not the first one on the top, but the second one. That's why I put the No Photo logo here, but it is under review. So actually, it is a paper that will be published really soon. So here you can see the detection of the occultation, so when it goes behind the star, of TRAPPIST-1b, which is the first exoplanet. And so it is the first time where you can see actually the emission of a temperate rocky exoplanet. This is at 15 micron, and it has been published by Thomas Green at NASA Ames. And what's really interesting, when you go the emission, you have a direct constraint on the temperature. Here on the bottom is the same detection, but at 12.8 micron. And so to actually achieve this, we had to observe 5 occultations, 5 eclipses. So we had 5 times going around the star, and then we stacked all the observations to have the signal to noise ratio high enough to detect it. So now we have 2 photometric channels. So the question behind this is, can we constrain the presence of an atmosphere? So if you put these 2 points here on a spectrum, so obviously it is not a spectrum, it is just 2 points, but you can start constraining the scenarios. So depending on models that you can do. So here on the left, you have different models of the rocks of this exoplanet. So likely the rocks that could be at the surface. So we tried ultramafic rocks, but also oxidized works with different albedos and simple black bodies as well. And so you have some scenarios that could actually match both points. And the one that matches is the presence of ultramafic rocks, right? And so then you can imagine that we have still an atmosphere. So obviously it won't be an extended one because we would have seen it with previous observations, but it could be a tiny atmosphere. And so there is one scenario that could actually match the 2 points, is a thick atmosphere of CO2 with the presence of hazes. And so this is 2 possibilities. So obviously we do not have the answer yet, but it is a first start of a characterization of a temperate rocky exoplanet. So I want to give a last example before I move to my work. And this one is on a giant young exoplanet. So it is not close to the star, but still far enough to be imaged. And so we did coronographic observations. So I wanted to show you how coronographic results look like. So this is a system which is called HR8799, and you can see different exoplanets. So you have B, C, D, and E. So here they are, B, C, D, and E. And so when you actually put the mask on the star, you reveal the presence of the planets. And so when you extract the emission flux of them, you can put them on a diagram showing a spectrum. And so you had previous observations, and now you have the 3 James Webb points here in the infrared, constraining actually the temperature of this young Jupiter. So again, this is the first time doing it. So we can't really conclude for now as the formation of this planet, but we actually start doing it with James Webb, and more importantly, in the mid-infrared, where you can actually discriminate the temperature of the planet and the gravity. So now let me move to my work, which is the role of what we call photochemistry in exoplanetary atmospheres. So what I did during my thesis, I observed WASP-107b, which is what we call a super Neptune. And so here is an artistic view of it. So here is the planet. It is a hydrogen-helium dominated exoplanet. So it's a gaseous one, and it is orbiting, here you can see the star. So let me tell you more about this planet. It is what we call a Neptune. So it is 30 Earth masses, but it has the radius of Jupiter. So it is a very, very inflated exoplanet. And you can see the period is really short, 5 days, 5.7 days. It has what we call a low equilibrium temperature. So it is 740 Kelvin. So for these exoplanets that are really, really close to the star, we expect the temperature to be really high. So this hot Jupiter, for example, they have a temperature like going to 1000 Kelvin. But in our case, it is lower than that. It's 700. The gravity is really low, 260 centimeter per second squared. So it's very low gravity. It has been shown that it is irradiated, that it has eroding tail of helium. So it is here another artistic view of it where you can see this loss of mass of exoplanets. And we had before, this is the only spectrum we had before. So this is a Hubble spectrum. And so what was shown here is the presence, of water vapor. Obviously, this is the water wavelength range, and the presence of condensates at high altitude. But this is what we had before. And so what we did is that we observed the transit of this. It was observed last year in January. The transit lasts about 2 hours and a half, but when you observe it, you always take a range before and after. So the whole observation was 8 hours. We used the MIRI instrument and the low resolution spectrometer. And here is the white light curve. So this is the transit we observed. And I wanted to point out the quality of the data. So for those who are familiar with data reduction and observing with all kinds of telescopes, we all know how hard it is to observe an object, right? If you observe from the ground, you know, there is this all atmospheric variabilities, but when you observe from the space, you know, there is jitter, there is a lot of instrumental systematics. But in the case of James Webb, we have this incredible stability where you can actually have this curve without any correction. So this is what I wanted to show because it's kind of very easy for an astronomer to work with this kind of data. So now let's move to the spectrum we extracted. So here is the spectrum. So it goes from 5 to 12 micron in the mid-infrared. And we used different techniques of reduction techniques. We actually used 3 different reduction techniques. And so when we obtained this spectrum, we already saw that there is something happening, but we don't really know what it is. And so to actually constrain the composition of it, what we did is that we run what we call retrievals, which are atmospheric models that we invert on the data to fit the data. And so we used 2 different setups. So the 2 ones are here. There is the one in orange and there is the one in blue. And we just separated them here so that you can see them clearly. And so what these retrievals reveal in the atmosphere of this exoplanet is the presence of, here you can see SO2. And SO2 is sulfur dioxide, and it was absolutely not predicted. I mean, with the model we did before, I would never thought there would have been SO2 in this atmosphere. Actually, I would have expected methane because this is what we expect at this temperature, but we didn't see it. And also, you can see here in yellow, the contribution that shapes completely the spectrum, which is a contribution of clouds. And so I want also to show you the significance of this detection. So what we can see here on the left is how the model actually fits the data and how well it fits the data. And so this is what we call the significance. And you can see we have really high significance for the water vapor, for the sulfur dioxide. And what you can see here is that the models, including clouds and silicate clouds, are favored over more simple cloud setups or no clouds at all. On the right it is what we call the volume mixing ratio, which is kind of the value that shows the abundance of these molecules in the atmosphere. So I wanted to show you here what the SO2 looks like when you look at the spectrum. And so what you can see here is the two fundamental vibration bands of the molecule of SO2, so nu3 and nu1. And so this is exactly what you see in the mid-infrared when observing this exoplanet. So when you observe SO2 and you don't expect to see it, you want to understand why you have this, as we know that sulfur dioxide exists in our solar system, right? So what happens is that last year, another group, which is the early release science, discovered SO2, but in another exoplanet, which is WASP-39b. And so WASP-39b, you have the spectrum here. You had this SO2 here that is discovered at shorter wavelength range. But the difference with this exoplanet is that it is really hot, 1000 Kelvin, and receives higher flux. So we do expect sulfur to be in the form of SO2 in this exoplanet. But for cooler exoplanets such as WASP-107b, we don't expect it to be in this form, but we expect hydrogen sulfide, H2S. But this is not what we found. So the question is, how can you form SO2 in warm super Neptune? And so this is what we tried to do. So the answer is, what happens is a process of photochemistry. So let me show you an example of an atmosphere here. So you can see the pressure that decreases with the altitude, and here the temperature. So on the left, this is what we call a pressure temperature profile. So the temperature and the pressure varies as a function of altitude, and the temperature is varying a lot, and sometimes it has inversions. So you can see the inversion of the temperature here. And so what you sound when you sound with MIRI is this range here. When you sound the upper atmosphere, where you can have the escape and the photochemistry, and this range here, where you can have all the molecules that you're sounding, and also the clouds and circulation. So this is what we sound with the MIRI wavelength range. And so what we found is that in the upper atmosphere, you have photochemistry. So just to show you what photochemistry is the fact that you have incident photons that are really energetic, that are going to break the bounds of the water vapor that is in the upper atmosphere and to dissociate it. And the hydroxide here and also the atomic hydrogen that is produced is going to oxidize the H2S. And then you have a series of reactions leading to the formation of SO2 here. And so this is what happens. So we created models of atmospheres. And what we found is that if you do not put photochemistry in the model, you do not produce here an amount of SO2 that is detectable. But on the contrary, when you put photochemistry, you actually start increasing the amount of SO2 that you produce. And this amount of SO2 is increasing with what we call metallicity. So all the elements that are more metallic than hydrogen and helium. And so we prove through models that what we have in this atmosphere is actually photochemistry. And the final thing that I wanted to show you is that what I didn't understand actually was the fact that this atmosphere is quite warmer and receives really less flux than expected. So how is it possible that you do have photochemistry? So we did a bunch of simulations playing around with the gravity or with the radiation. And so what we see here, when you increase the gravity, your scale height decreases. So the UVs do not penetrate really well in the upper atmosphere. And so this is why the SO2 is not really well produced. And so you decrease the amount of SO2, whereas when you have low gravity, you can actually penetrate really well deep in the atmosphere, and you increase the amount of SO2 that you produce. So there is this link with gravity. And also, what is really interesting here is that we increased the irradiation. So we took for example, the aeration of the other planet where you have actually SO2 that has been discovered. And what you can see here in purple is the curve of SO2 that has been discovered, and this SO2 is lower than expected. And so what happens here is that if you increase the flux a lot more than what it is, you dissociate the SO2 as well. And so the reason why you have photochemistry in this warm super Neptune is because you have a moderate UV radiation, and you have a low far UV near UV ratio, and a low gravity. And all of these conditions make it possible for the SO2 to be produced and maintained in this atmosphere. So I am not going to go further in this because it's a very long topic, and I don't want to take more time to talk about it, but I'm just going to give my conclusions and some perspectives. So I wanted to say that JWST, as you can see here, offers a unique opportunity to study exoplanets. You have finally an observatory in the near and mid-infrared. You have a very high sensitivity with this huge mirror where you can actually sound low mass exoplanets, and obviously an excellent pointing stability for the transit method. You have a very huge diversity of observing modes, and for the MIRI, so the mid-infrared imager and instrument, you have detection of the isotopologues, which is the first one, the first detection of the thermal emission of a temperate rocky exoplanet, the detection of SO2 and the two fundamental vibration bands, and the first detection of silicate clouds in the mid-infrared. So this is a very strong result. And for my perspective, so I want to understand the photochemistry of these atmospheres. This is the goal I have. So I want to understand the conditions of it, irradiation conditions, gravity conditions. And so I am carrying on this work. So I am working with Professor Rance Waters on JWST Cycle 2 accepted programs on this to carry on this work. And on temperate rocky exoplanets, so there are different JWST accepted proposals to actually observe the more of these TRAPPIST-1b and C exoplanets. And of course, if we can, investigate the rock compositions of these temperate rocky exoplanets. And that's all. Thank you very much for listening to me. I hope I was not too long. And please, if you have questions, I'd be happy to take them.
Thank you very much, Achrène, for your excellent talk. Please, question from audience.
May I ask one?
Yes, of course.
Yes, Vadim Kaidash. Thank you again. Nice talk. And I'm interested in what kind of model exactly you use for comparison with observational data. What model?
Okay, so what we do is we use, in this case, a 1D model that solves the equilibrium state because we have taken different layers in the atmosphere, and so we solve the equations. And what we do is that we take equilibrium models and we inject disequilibrium processes. So we use vertical mixing through eddy diffusion. We incorporate the chemistry, so the kinetics of the chemistry that could happen and the mixing. And so this model is a good one, but to my mind, it's not enough because it's a 1D. So you kind of remove all the 2D and 3D effects. And one of the effects that is not included is the horizontal mixing. So if you have horizontal mixing. So this is the model we use. And so we use the carbon, hydrogen, nitrogen, and sulfur chemistry. Yeah, this is the different chemistry we use.
Okay, this is radiative transfer 1D with different components.
Radiative transfer 1D, yes.
Thank you very much.
Thank you, Vadim. Please, More questions? I have one also. What about silicate clouds? Why the nature of these clouds is silicate? There is some signature of silicate in the spectrum, or what reason?
Yes. Okay, maybe I can show it back. It would be easier here. No, maybe this one. Okay, so here is the spectrum. So you see in yellow, this is the signature of the silicate clouds. So, okay, this is a bit tricky. Why? Because generally the clouds would modify the shape of the spectrum. So either it would decrease the size of the signatures, or it would change the shape. So you can't really tell by a signature that it is clouds. So what happens here is that this result is completely model dependent. So what we do is we do Bayesian statistics. So we take different models, simple clouds, no clouds, silicate clouds, and we compare through the Bayes factor these different models and the fits to the data. And so what happens here is that the silicate clouds are favored over other setups and other models. So this is completely model dependent. And so if I may add something, what we should do here is extend the wavelength range through the optical. So use James Webb with all the other instruments from the near to the mid-infrared, because in the optical, you also have signatures of clouds. You have the scattering that you can see, or the hazes. And if you have that, you can constrain through the data a bit more than just using the MIRI range. So,
thank you.
yeah.
I understand now. And another question also about the silicate clouds. There is something information about the level of these clouds and how these clouds can heat the atmosphere.
Yeah. So the retrieval showed that it is at 10 to the minus 5 bar. And so this is the retrievals giving it. So it is always tricky because it is model dependent, right? It depends on the particles that you use in your model, the size of the particles you put, and the interaction between these clouds and the rest of the atmosphere. So it's always tricky to actually give like a bright value to it. But yes, we expect them to be at 10 to the minus 5. And this is interesting because it's giving like a cloud deck. And we didn't find methane, for example. And we expect methane in the atmosphere because it's quite warm at 700 Kelvin. And so maybe the methane is above the cloud deck. So maybe this is what's going on, but we don't know yet. And we do expect data at shorter wavelength range to like answer the question and be sure of it.
Okay, thank you. One more time. Please, another question.
Can I ask you? Thank you very much for your lecture. Very pleasure to hear about exoplanet, because it's not so native aims for our group in Kharkiv. And so very much to know about the different bodies out of the solar system. And my question, you used the biggest and more advanced technique for observation of these bodies. And what about limited magnitude that you can use to obtain it so good spectra for the exoplanet, and have limited magnitude for Webb telescope?
Okay. So the magnitude, the limit, I don't know the amount of the magnitude I can use. So you mean the highest magnitude that we can reach?
Yes, because you can use the bright star, I understand, but how is you can use the smaller one? And,
yes. So actually, we can go pretty far. I don't know the value exactly, but what we can do. So James Webb has been designed to observe galaxies first. So it is made for very faint objects, such as the first primordial galaxies. So we can observe M dwarfs really well, actually, with James Webb. I don't know if this is the question. This is the kind of object we can observe a lot, and actually, this is really great because this is one way of detecting exoplanets and smaller exoplanets. So it's a right way to characterize this kind of exoplanets. So yes, and the exact value I just don't know for the magnitude.
Used also the Webb also used for the light curve observation for transit curve, and in this case you can use as much as possible to smaller object to find, and very precise transit curves. And interesting that what is difference between the brighter star and smaller object, if you know how different between them.
Yeah, so the thing is, if you have a very bright star and a small exoplanet, your transit depth is going to be really small, because you have, it's geometry. You have a disk and another disk, and so if you cover a very small surface of it, it's going to be really tiny. And it's not only geometrical, you have the emission of the planet itself. And so if you have a very bright star, the amount of emission brought by the exoplanet is going to be very, very small. And so you will be dominated by the star. And more than that, a star is really active. And so over time, you have all the stellar variabilities. And this is a problem. And so by observing smaller stars, you could increase the transit depths. And if you observe it in the mid-infrared, you will increase the emission of the planet because it's a cold body. So the peak of the emission is in the mid-infrared. And so this is a right way to actually do that. And stellar activity is less visible in the infrared. So that's why we do go for these stars that are not really bright. And I don't know if I answered the question.
I see. The light curves, short note, the light curves that you showed, it's light curves obtained in a very narrow band, where you expected the change of a planet. You change during transit, change the spectra because you have something spatial emission for planet, and so on that transit light curves we saw the change of visibility of planets.
This is, are you talking about? Okay.
It's another one question. Yes, this one, but okay. There is another one with small.
Yes, I can see. Yes, I see what you mean. Okay, let me find it. Okay. Almost there. This one?
Yes, this one. Yeah, it's the emission transit light curve. Yeah.
Yeah, it's okay. So what we observe here is when it goes behind the star. So first, what we have to know about these exoplanets, they're really close to the star. So they're facing tidal effects, which means that it's like the moon and the Earth. They're the orbit is synchronized. And so it is always giving the same face to the star. So there is one face really hot, really irradiated, and there is one that never sees the stellar light. And so when it goes behind it, just before it goes behind the star, you will see actually the emission, like the day side. And this one is really hot, so you can actually measure the value. This is what we do. But this is just because it is tidally locked and it is really heated in one side. If you have an atmosphere, you would actually circulate the heat, recirculate the heat, and you wouldn't see this shape that well. And so we are kind of lucky because this one is really heated, and so you can see it. And that's why we observe the temperature. And actually the temperature of this planet in the daytime is 300 degrees, yes. So it's hot. It's hotter than the Earth. But it's the first one of the 7, so I mean I would expect this to be really high. Is it
this is special case, and it's interesting.
It's a very special case.
Yeah.
Yes,
Thank
exactly.
You. Okay.
You're
Thank you very much.
Thank you. Irina Kulik also have a question. Please, Irina.
Thank you very much for your presentation. And my question is similar to previous one. When you analyze the transits at different wavelengths, did you pay any attention on the transit shape? Is there some useful information?
Yes, sure. Okay, let me show you back this one maybe. Okay, so what's really interesting here is obviously the shape here. So there is something what we call the limb darkening, which is the fact that the stellar disk, it is an observer problem, is not as bright on the limbs than in the center. And so that will completely modify the shape of the transit. And this is something we really pay attention to because you can extract a wrong value of flux just because the limbs are darker, but it's just a visual effect. So this is something we do. And also what you can do, this shape here, this is what we call the ingress and the egress, is something where you can actually see the planet coming in front of the star, and so you can see the different parts of the planet. So you just take the time to actually separate what's happening here from here, and so you can see things happening. And this is what we can call limb asymmetries. And sometimes as you have heat recirculating, you can see on the one side, you can see the clouds of the planet, on the other side, you can see the hot spot. Because there is this circulation, and as you don't see always the same side at the entrance of the transit and the when it goes out. This is something we do, and it's really interesting. This is something we do, it's the second step. I mean, we don't do that at first, we do that after. So now we're in the middle of this kind of analysis, for example. I don't know if it answered the question or it was more about stellar effects.
No, okay, thank you very much. And my next questions about the data. I am not familiar with this. Are the data in the open access, or it is closed for your community?
Okay, so there are different categories of data. The ones that are always in access is the early release science. So it was made for it. So you can find any kinds of data, not only on exoplanets, but on any kind of objects, going from galaxies to exoplanets. It's very wide, and solar system as well. So this is completely available. And then when you have observations like this, so guaranteed time or general observers, you have 1 year of propriety, and then it goes public. So for example, this one is public now because we asked it to be public when we published the paper this year. So you can just go on the archive, which is called the MAST, M-A-S-T, and you can ask for any object and then download the data. So yeah, it is available.
Thank you. Any other questions, please? I have one stupid question. How close we are now to the data about winds on the exoplanets? How data from James Webb can help us see the circulation in atmospheres of exoplanet?
So this is what we call a phase curve. I don't have any example here. Okay, see, let me show you one example. It's a slide that is, I didn't show it because I have too much to say. Okay, maybe this one. Okay, can you see it?
Mm-hmm.
Okay, so what happens is that, so you have your planet orbiting around, and it is tidally locked, right?
Mm-hmm.
So when it is in front of it, you see the night side. And as much as you go behind it, you start seeing the day side. And so your flux, planetary flux, only increases, okay? So this is what we call a phase curve. And so depending on the amplitude of the phase curve, you can see the amount of circulation. So if there is circulation, you have heat that is distributed over the whole atmosphere, so you won't have much variations. But if there is no circulation, you have a very strong day side and a very strong night side, and so you will have a very strong phase curve. So this is something we can do to measure it. Of course, it is model dependent because it's not only about circulation, but there is the albedo as well playing around. So it depends on the quantity that your atmosphere is able to reflect. And so it is always tricky to know if it's circulation or reflection. But if you observe in different wavelength range, so in the visible or in the infrared, you would access either the reflection or the emission. And so you can start constraining it. And this is how we do now.
Mm-hmm. Thank you. Now I understand better. If there is no question, let's thank again our speaker from France. Thank you very much, Achrène, for your nice and interesting talk.
Thank you very much for having me.
Thank you.
Thank you.
Bye.
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 Bye.